now we'll start an important topic. This is coset, and this topic is basically given in the same syllabus, Calcutta University syllabus, Unit 2. So here we'll do the cosets and properties of cosets, and we will do some few examples and the Lagrange's theorem. Mainly, we will discuss the important problem related to the coset topic. So now we'll start with the definition of coset in algebra. So first we'll define. So here the question is, this is question number 41. So define cosets. So how to define coset? Here first we'll define the left coset and right coset. So let G be an group, G be any group, and H be a subgroup of G, and H be a subgroup of G. So G is a group and H is basically subgroup of G. Then a left coset of H, in G is defined as AH equals to a small h such that small h belongs to capital H. What is A? For some where A belongs to G. This is the left coset. And here also define the right coset. And then a right coset of H in G is defined as HA equals to HA such that H belongs to capital H. And what is A? Where A is an element of the group. So here actually we define two cosets with respect to an element. A belongs to G. One is basically AH, where H is a subgroup of G. And we define HA. So H, here we just multiple A from the left side. So A small h belongs to capital H. And HA, that means small h belongs to. Here just we multiple H by A from the right side. Okay, so this is called the left coset. And this is basically the right coset. So this is our solution, how to define a coset. It may be left coset or right coset in a group. Now we'll come to some example, how to give an example of left coset and right coset. So here example 1. So let G is basically Z plus. We know set of all integers with respect to addition forms a group. And we take a subgroup H. This is basically 3Z plus. Now the cosets of H, say here, if we take the coset an element, say, then 0 plus H, that we can define in that way. 3n such that n belongs to Z. And 1 plus H, because this is a group with respect to addition. This is 1 plus 3n such that n belongs to Z, and 2 plus H, that means 2 plus 3n, n belongs to Z. So you can define 3 plus H also. 3 plus H, where 0, 1, 2, 3 are element of G, that means they are integers. So 3 plus H, it will be 3 plus 3n, such that n belongs to Z. And that also you can write 3 into 1 plus n, such that n belongs to Z. And this is exactly same as some 3k, such that k equals to 1 plus n. This is also belongs to Z. And this is exactly 0 plus h. Again, you will check 4 plus h, that will be again 1 plus h. So that means these are the, that means there are 3 distinct left coset of h. There are 3 distinct left cosets of h in G, and they are 0 plus h, that means h itself, 1 plus h, and 2 plus h. Now we'll do some problem. The problem is basically asked in the year of 2004, Calcutta Honors Examination, B.Sc Mathematics. The question is question number 40, true or false? True or false? Justify. So what was the question? The question is any two, the statement is any two left coset of a subgroup of a group are either disjoint or same, or either disjoint or identical, or you can say same. So this is a statement. You need to prove statement is true or false, and this question is given for 2 marks. The Calcutta University B.Sc examination. So now we'll solve the question. So now we'll come to the solution. And here the statement is true. So we'll say the statement is true. But okay, we need justification. So what we will take? We will take any two cosets. So what is exactly given? I just assume let G be a group, and capital H be a subgroup of G. And what we have to prove? We have to prove it is either distinct or identical. So first we just here consider they are basically let A comma B belongs to G. We have taken 2 elements, G, and the subgroup is basically H. We take any 2 element A, one element is A, another element is B, with AH intersection BH, this is not equal to 5. So that means they have a common element, and from that we just show, in that case, we shall show that if they have one common element, that means they are not disjoint. So in that case, so they are basically same. So obviously, if you take two left coset, one is AH, that means a small h such that h belongs to capital H, another element with respect to B. This is basically another left coset BH. H belongs to H. So two cases will arise, either H intersection BH equals to 5 or H not equals to BH intersection BH not equals to 5. So in that case, if we will show H equals to BH, so what do we have proved? We have proved either this is disjoint or these are same. Okay. So that's why if we take AB belongs to G such that the two left coset are basically dot distinct, and from that we will show that okay they are basically same. So if we show H equals to BH, first we will show H subset BH, and second we will show H BH also subset of H. So since H intersection BH is basically non-empty, so there exists an element C belongs to H intersection BH. Okay, for some C belongs to G. So obviously that implies C belongs to H and C also belongs to BH. And from that we can write C equals to some AH1 and also C belongs to B. That means we can write some BH2 for some H1, H2 belongs to H. And from that what we can write? We can write A equals to from this relation we can write A equals to B H2 H1 inverse and B equals to AH1 H2 inverse. That we can, because since H1 H2 belongs to H and H is subset of G, so H1 inverse and H2 inverse, that is also belongs to H and this is also subset of, because H is a subgroup. Okay, so that we can say. Now what we will show? We will show H subset of BH. Now we will show AH subset of BH and we will show also BH subset of H. So that we will consider 1 and that we will consider 2. So therefore from 1 and 2, what we say, we conclude H equals to BH. That we will conclude. So, but the thing is, how we will show H, that left coset is subset of another left coset of BH. So, how will show? Let an element D belongs to H. So, D belongs to H, that means then D equals to some H3 for some H3 belongs to H. So now A, that we can write, since what is A equals to BH to H1 inverse. In position of A, we can write BH to H1 inverse H3. Okay, because since A equals to BH to H1 inverse. Okay, so that means what we can write, that is B H2 H1 inverse H3. This is by associativity, and that is belongs to BH. Why? Because since H is a subgroup and all the elements H2, H1 and H3, since H1, H2, H3, H1 inverse all belongs to H, that implies with the help of closure property H2, H1 inverse H3 belongs to H. So that implies D belongs to H, therefore D belongs to H, that implies D belongs to BH. Since D is arbitrary, so what we can say? We can say H subset of BH. Again, we will take an element from BH. So let some element G belongs to BH. Then what we can write? G equals to BH4. BH4 for some H4 belongs to H. What is the meaning of B? B is here. B means AH1 is to inverse. So that we'll put here. AH1 is to inverse H4. Since B equals to AH1 is to inverse. So from that we can write A. H1 is to inverse H4. Again by associativity. Associativity. And that belongs to AH. Why? Because since H1 is to inverse H4, all R belongs to H. As by H is a subgroup, closure property holds. So we can say, so what we get here, G belongs to BH. That implies G belongs to H. Okay. And from that we can say B is subset of H. Since G belongs to BH, that is arbitrary. So from 1 and 2, what we can write? H equals to BH. That means any two left coset. So therefore, any two left coset of a subgroup of a group is either disjoint or self. That he conclude. Now we will come to the next important problem. This question is given of 2007. So this is question number 43. Let H be a subgroup of a group G. So show that two left coset H in G, two left cosets H in G are either disjoint or identical. Now again, there is a further question. If order of G, this is equals to N, and that is finite, and this is finite, then show that any two left cosets of H in G, any two left cosets of H in G have the same number of elements. Have the same number of elements. So this is basically 2 plus 3, 5 marks question. So now we will come to the solution. That is two part of the question paper. First it is given H is a subgroup of G. What will show? Two left coset of H in G either disjoint or identical. That part we have already done in the previous problem. Okay. Any two left coset of a subgroup of a group is either disjoint or distinct or same. So obviously I will write here the first part of the question paper. This is done. Just you copy the previous one and paste here. So that will be your answer of the first part. Now the second part, this is the first part, this is the second part. If order of G equals to N is finite, then show that any two left coset of H in G have the same number of elements. So the second part, What is given? Order of G, this is given n, and n is basically finite number. And it is given H is a subgroup of G. And from that, what we have to show? We have to show that any two left coset of H in G, any two left cosets of H in G have the same number of elements. Have the same number of elements. That we have to show. Okay. So what we will do? We will take any two left coset and we will show that they have the same cardinality. So just we will consider let H and BH be two left coset of H. This is a small h, H belongs to capital H, and BH, that means B small h, H belongs to capital H, be any two left cosets of the subgroup H in G. What is A and B? Where A and B are the element of G. Now what we'll do, we'll define when we'll say two set with the same cardinality. So one set is B, one is A, another is B. When A and B are equipotent set, they have same cardinality. If and only have the recall is they are the same cardinality, the cardinality will be same. Okay, let's say N. So there exists a bijective mapping A from A to B. So what we will do here, we will define a bijective map. After that, we can conclude. We can define a map which is bijective from H to BH, and from that we can conclude H and BH have the same cardinality. So we define a map, mapping if H to BH by f of H equals to BH for all H belongs to H. This is our map. So this is our left coset AH1, AH2, maybe AHN like this. So this is our H, and this is BH. That means BH1, BH2, BHN. So H1. In that way, we just define the map. Now we'll check this map is bijective. So first, what we'll check? So what will be our step 1? So first we'll check. We have to show that if H to BH, this is injective. This map is injective. Okay. So what we'll do? Let us two distinct elements. Say here H1 and H2. Let AH1 not equals to AH2, and AH1 and AH2 both are the element of H. Okay, we have just taken the distinct element. Okay, so we can take, we will take in that way, let AH1, AH2 belongs to H be such that f of AH1 equals to f of AH2. And from that, what we can say? Now, f of AH1 equals to f of AH2. It is defined f of H equals to B. So this is defined, that implies BH1 equals to BH2. And if we use the left cancellation law, so it will be H1 equals to H2. This is by left cancellation. You know, in a group, left cancellation law must hold. And from that, again, we can write AH1 equals to AH2. So what we have proved here, f of AH1 equals to f of AH2, that implies AH1 equals to AH2. So that means if H to BH, this map is injective. Again, we will prove F is surjective. So what is our step 2? We have to prove that if H to BH is surjective. How we will show it is a surjective map? So this is H and this is basically BH. So we will take an element from here. So the element is B. We will show a pre-image. This is exist here. So let we will choose an arbitrary element BH belongs to B capital H. Okay. Then this shows that then what we can say according to the definition of map, f of H equals to BH. So this element basically H. So thus what we have seen, f of H equals to BH, where H belongs to a capital H, and since H belongs to capital H. That implies H is a pre-image of BH. H belongs to a capital H is a pre-image of BH. So that means every element in the codomain set must have a pre-image. Therefore, every element in the codomain set BH has a pre-image in the domain set H, and hence if map H to BH, that map is surjective. So by step 1 and step 2, what we have proved here, therefore by step 1 and step 2, we say that if H to BH, that map is bijective map. And therefore, the cardinality of the set H equals to the cardinality of the set BH. Thus, we can conclude any two left cosets of the finite group G has same cardinality. Now, we will define two important sets. So this is important to recall. So let G be a group and H be a subgroup of G. Okay. Define to set, define script L. So that means H such that A belongs to. What exactly mean? This is basically the set of all left cosets of H in G. And we also define another set script R. This is basically HA such that A belongs to G. And this is called the set of all right cosets of H in G. And the important recall is then the cardinality of the set is script L. This is the cardinality of the set R. So that means the number of left cosets of H in G, this is equals to the number of right cosets of H in G. But how to prove the number of left coset and number of right coset? That question asked in the year of 2011. This is question number 44. What was the question? The question is, let H be a subgroup of a group. H is a subgroup of a group G. Prove that the set of all left coset of H in G, left cosets of H in G, and the set of all right cosets of H in G have the same cardinality. And this is for 4 marks question. How to prove the set of all left coset of H in G and the set of all right coset of H in G are of the same cardinality. So now I'll come to the solution. So what is given? Given H is a subgroup of a group G. Okay, so this is our group and this is basically subgroup H. So we define the set, define script L. This is H such that A belongs to G. That means this is basically set of all left cosets of H in G. Define script R. This is basically HA. A belongs to G. Set of all right cosets of H in G. What we have to show? We have to show that cardinality of L equals to cardinality of R. That is, number of left coset and number of right coset are basically same. How will show? Just previously we have shown number of element into distinct left coset are same. Here how the set A cardinality will be set B cardinality if and only if there exists a bijective map. Bijective map F from A to B. Similarly, we will define a map which map is bijective, and from that we can show the cardinality are basically same. So we consider the map. Okay. So we consider the map. Consider a map A from L to R by f of AH equals to HA inverse. What is A? A is an element of G. Just to define the map in that way. But here we will define first well defined, because this is not commonly known map. So first we will show if is well defined. So how we will show? We will show for well defined, we have to show that for well defined, we have to show that for all AB belongs to G, H equals to BH. That implies HA inverse equals to HB inverse. Okay. So why you just recall these basic facts? The fact is, f is a function from A to B is well defined if and only if for all xy belongs to A, x equals to y implies fx equals to f. That is the definition of well defined. Okay, that we have to show. So we'll take any A B belongs to G with AH equals to BH. Now since A belongs to AH and AH also equals to BH, that means A belongs to BH. That implies A equals to BH for some H belongs to H. And hence you just take inverse on the both sides. So A inverse will be H inverse B inverse. So by the standard property, since in a group AB whole inverse equals to B inverse A inverse for all AB belongs to G. Okay. So this relation will holds. Now we'll we'll show H inverse equals to HB inverse. So take any, say, alpha belongs to HA inverse. So then that alpha can be written as some XA inverse for some X belongs to H. Therefore, alpha equals to XA inverse, and inverse means H inverse B inverse. So X H inverse B inverse, and that we can write X H inverse B inverse, and that belongs to H B inverse. H B inverse. Why? Because since X H inverse both belongs to H, that implies by the closure property X H inverse belongs to H. So what we have shown here, alpha belongs to, we have taken alpha from H A inverse. That implies alpha belongs to H B inverse. And that implies, so therefore, H A inverse subset of H B inverse. So this is 1. And since alpha belongs to H inverse is arbitrary. Okay. Now we will do the reverse case. So conversely let beta belongs to HB inverse. So then what we can write? Beta equals to some YB inverse for some Y belongs to H. So therefore beta equals to YB inverse, and here B inverse is B inverse. From that we can write B inverse equals to H inverse B inverse. Since A inverse equals to H inverse B inverse, so that implies B inverse equals to H A inverse. So that we can write Y into B inverse means H A inverse. Why this is the argument. So from that we can write by associative law Y H A inverse, and that belongs to H A inverse. Why? Because since Y and H both belongs to H, that implies by closure property YH belongs to H. So that means beta belongs to H A B inverse. That implies beta belongs to H A inverse. So therefore we can say H B inverse subset of H A inverse. And since beta belongs to H B inverse, this is arbitrary. This is 2. So therefore from 1 and 2, what we conclude? We say that H A inverse equals to H B inverse. Okay. So we have to show that for all AB belongs to G, H equals to BH implies H A inverse equals to H B inverse. So that means our function, therefore, if function L to R, set of all left coset to right coset, that function is well defined. Now we will prove injective. So we have to show that next for injective, what we will do, we have to show that if L to R, this is injective 1 to 1. That we have to show. Okay, how we will show? We will show here. Let set of all left coset is basically in the form let L1, L2 belongs to L be such that f of L1 equals to f of L2. Okay. Now, what we will show? We will show f of L1 equals to f of L2 implies L1 equals to L2. Now, since L1, L2 both belongs to L, so that implies L1 equals to the left coset, so H, for some A belongs to G, and L2 equals to BH for some B belongs to G. And the thing, since f of L1 equals to f of L2, so that implies f of L1, that means f of H equals to f of BH, and that implies H A inverse equals to H B inverse. Okay. And from that we can write, therefore A inverse equals to E A inverse that we can write because it is the identity element that belongs to H A inverse, and H inverse equals to H B inverse. So that means what we get here. So here we get A inverse belongs to H B inverse, and that implies A inverse equals to H B inverse for some H belongs to H. And from that we can write A equals to, if we take both side inverse, so inverse, this is equals to HB inverse. Inverse means A, B inverse in B, so BH inverse. Okay, so this is just the star marks. Now what we will show? We will show f of L1 equals to f of L2 equals to L1 equals to L2. So our target is to show L1 equals to L2. Our target is therefore f of L1 equals to f of L2 implies L1 equals to L2, and hence we can say if L2 R, this is injective 1 1. So L1 equals to L2, that means what we will show? We will show L1 subset of L2, that will be 3, and again we will show in the back calculation L2 subset of L1, this is 4, and therefore from 3 and 4 we conclude that L1 equals to L2. So how will you say L1? So take an element, then the element say X belongs to L1. So then X belongs to L1 means AH, since L1 equals to AH. Okay, here we have written L1 equals to H. And from that, what we can write? We can write, so X equals to AH1 for some H1 belongs to H. What is the meaning of A here? A is basically BH inverse. So we'll put BH inverse H1 by star. By associative law, we can write BH inverse H1. Okay, and that belongs to BH. Since H inverse H1 belongs to H, as H inverse H1 both belongs to H, and H is a subgroup, and BH is basically L2. So that implies BH is basically L2. So that implies, therefore X belongs to L1 implies X belongs to L2. So that means L1 subset of L2. Again, let Y belongs to L2. And what is L2? Then Y belongs to BH, because since L2 equals to BH. Okay. Now we'll show here Y belongs to L1. So Y belongs to BH. That means we can write Y equals to BH3. BH3 for some H3 belongs to H. Now BH3, that we can write. So here you will see B means, here we can write, since A equals to BH inverse. Since A equals to BH inverse. So that means B equals to AH. We will put here AH H3. And that is basically AH H3. And that is basically belongs to H. And H means L1. So therefore, Y belongs to L2 implies Y belongs to L1. And from that we can write L2 subset L1, since Y belongs to L2 is arbitrary. So what we can conclude? L1 subset L2, L2 subset of L1. That means L1 equals to L2. That means f of L1 equals to f of L2 implies L1 equals to L2 and hence if L2R is injective. Now we'll come to the surjective part. That means now we'll prove the map is, we have to show that the map F set of all left coset to set of all right cosets is surjective. How will show surjective? Will show every element in the codomain set must have a preimage. Okay, so this is set of all left coset. This is set of all right coset. We will take a right coset here, say R, and so there exists L such that F of L. So that is, we have to show that for all R belongs to set of all right coset, there exists L belongs to script L such that f of L equals to R. That we have to show. So take any R belongs to, so R means set of all right coset. So then R must be of the form Hx for some x belongs to G. Now we'll choose L equals to x inverse H, and this is basically belongs to L because it is a left coset. And since x belongs to G, that implies x inverse belongs to G as G is a group. So therefore, here you just see f of L will be H f of x inverse H, and that will be, according to the definition of map, Hx inverse. So this will be Hx, and this is basically R. So that means R has a preimage. Since R is arbitrary, so that's we can write F is surjective. So what we proved here, F is surjective. Initially proved F is injective. So thus it is our conclusion, F script L to R, set of a left coset to set of a right coset is bijective. And hence we can conclude the cardinality are basically same. Okay, so this is our